Right now, as you're watching this, you're feeling time. Not thinking about it, feeling it. Your heart is beating. Your breath moves in and out. Somewhere in your body, you sense that this moment is different from the last one, and the next one will be different again. This feeling is so immediate, so obvious, that it seems like the most solid thing about existence. But here's where it gets interesting. When physicists describe how time actually works, the picture gets complicated. And I'm not talking about quantum weirdness or science fiction. I'm talking about the gap between how time feels and how physics describes it. So today we're going to explore that gap. Because understanding it doesn't make time less real. It makes your experience of it more profound. Let's start with the most obvious thing. You experience time as a flow. There's a past, things that happened. There's a now, this moment you're in right now. And there's a future, moments coming toward you. This sense of continuous flow is so strong that it shapes everything about how we think. We use time as a metaphor for everything. We say we're moving forward in life. We talk about being stuck in the past. We rush toward the future. These aren't just poetic phrases, they're how our minds naturally organize experience. But here's a question. Why do we experience time this way? The answer lies in evolution. Your ancestors lived in a world where flow mattered. Predators were coming toward them. Prey was running away. Seasons changed. Day became night. To survive, your brain had to develop an incredibly refined sense of causation, what happened because of what came before, and what that means for what comes next. Your sense of now is a biological feature. It's not a mistake. It's not an illusion. It's a tool that your brain built because it solved a real problem. How to navigate a world where causes matter, effects follow, and timing is everything. And it still solves that problem. Right now, you need to feel the flow of time to make sense of this video. To understand my words, you have to track which word came before and anticipate which comes next. So when we talk about time, we need to remember something crucial. Your intuition about time isn't wrong. It's just local. It works perfectly for the scale at which you live, seconds, minutes, hours, the human-sized world. But physics describes phenomena at every scale, from the speed of light to the quantum realm. And at those scales, time doesn't always behave the way your intuition expects. To understand why physics describes time differently, it helps to see how our picture of time has changed. For thousands of years, there was really only one way to think about time: Newton's way. Isaac Newton, in the 1680s, imagined time as something like an invisible river flowing at a constant rate everywhere in the universe. It's absolute. It's the same for everyone, everywhere. You could imagine all of space existing at once, but time as this separate thing moving through it. This picture was so intuitive, so powerful, that it lasted for more than 200 years. It matched observation. It predicted motion. It worked. Then, around 1900, something strange started happening in physics. Scientists noticed tiny discrepancies, little things that didn't quite fit Newton's picture. Not contradictions, exactly, just quirks. Inconsistencies. A German scientist named Michelson and an American named Morley conducted an experiment to measure the speed of light in different directions. Based on Newton's picture, they expected the speed to vary, to be faster in one direction, slower in another. But it didn't. The speed of light came out the same every way they measured it. That was weird. In 1905, a 26-year-old physicist named Albert Einstein was thinking about this problem. And he asked a radical question. What if the speed of light is actually constant for everyone, everywhere? What if we take that seriously as a fundamental rule of the universe? If that's true, Einstein realized, then something else has to be flexible. And that something is time. This was Einstein's great insight. Not that time is fake, but that time is woven together with space and motion in ways that Newton hadn't imagined. Time doesn't flow at the same rate for everyone. It depends on how fast you're moving. It depends on how strong gravity is around you. Now, this sounds like time is flexible or relative, and it is in a precise technical sense. But let me be crystal clear. Einstein didn't discover that time doesn't exist. He discovered that time is even more real and more intimately connected to the structure of the universe than Newton thought. This is an important distinction. The map changed. The territory did not. So let's talk about what modern physics actually says about time. And I want to be careful here, because there's a lot of misunderstanding about this. In Einstein's special relativity, the theory for objects moving at constant speeds, time is interwoven with space into something called spacetime. Picture it this way: you're not moving through time while standing still in space. You're always moving through spacetime in a specific way that combines your motion through space and your motion through time. Here's what that means in practice. If two observers are moving relative to each other, they will disagree on how much time has passed. Not by much. In everyday life, you'd need to be traveling at a significant fraction of the speed of light for the effect to be noticeable. But the effect is real. We've measured it. We've confirmed it with atomic clocks on fast-moving airplanes. Astronauts on the International Space Station age slightly slower than people on Earth, because they're moving faster through space. Again, this does not mean time is an illusion. It means that the rate at which time passes depends on your state of motion. Then, in Einstein's general relativity, the theory that includes gravity, time gets even more connected to the fabric of the universe. Massive objects bend space and time around them. And when you're in that bent space-time, time runs at a different rate. Clocks near the surface of a massive planet tick slower than clocks far away in space. We know this is real because GPS satellites have to account for it. If we didn't correct for the different rates of time at different altitudes, GPS would become useless within hours. Now, there's another area of physics where time behaves strangely: quantum mechanics. In the quantum realm, the world of atoms and particles, the mathematics treats time in a peculiar way. It doesn't have a special arrow. Equations can run forward or backward. The quantum laws don't prefer one direction of time. This is strange because your experience is entirely directional. You remember the past. You don't remember the future. Eggs break but don't unbreak. Time has an arrow for you. So why? Well, the answer probably involves something called entropy, the fact that systems naturally tend toward disorder. When you zoom in on individual particles, time is reversible. When you look at a collection of trillions of particles, the statistical tendency for disorder creates an arrow. The universe doesn't prefer the future, but the laws of probability do. Here's the crucial thing: none of this means time isn't real. All of it means time is woven into reality in ways that are deeper and stranger than everyday intuition suggests. I want to pause here and address some misunderstandings that are really common. You've probably heard someone say, time doesn't really exist, or the past, present, and future all exist at once, or time is an illusion. Sometimes physicists say things that sound like this, and it causes confusion. So let me be precise. When some physicists say, time doesn't exist, as a fundamental feature of reality, what they mean is, time is not a separate, invisible thing flowing through the universe. It's not background. It's woven into the fabric of space itself. The word exist is doing a lot of work in that sentence, and it's easy to misunderstand. What they do not mean: your experience of time is fake. Causation isn't real. You're not actually aging. Your memories don't actually correspond to things that happened. All of that is completely real. When physicists talk about the block universe, the idea that past, present, and future all exist equally in a four-dimensional structure, they're making a statement about what the math describes. But even in that picture, your experience of moving from past to future is real. Your perspective on that four-dimensional structure is real. Think of it this way: a book exists all at once. The first chapter and the last chapter are both physically there on the shelf. But when you read the book, you move through it sequentially. The book is real. Your reading experience is real. These aren't contradictory. The same is true for time. The mathematical structure that describes time is real. Your experience of time flowing is real. They're not contradictory. They're two different perspectives on the same thing. Here's another important point. Physics describes time mathematically. A mathematical description is not the same as describing what something truly is in some absolute sense. Math is a tool. It's a map. The map shows the structure of the territory, but the map is not the territory. When physics describes time in a certain way, it's saying, this mathematical structure makes accurate predictions about how things behave. It's not saying, therefore, your intuition is completely wrong, and this is how time really is underneath. So we're left with something interesting. There's a real gap between how time feels and how physics describes it. But that gap doesn't mean one of them is true and the other is false. It means they're operating at different levels. Your intuition about time is true at the scale where you live. When you make a decision, you expect your choice to affect the future, not the past. That's not a quirk of neurology, it's a real feature of how causation works in the everyday world. Physics describes time at every scale, including scales where your intuition breaks down. At those scales, time is not separate from space. Its passage rate varies. Its direction is not absolute. But these aren't contradictions. They're layers. Think about this. Water feels continuous and smooth to you. It seems like a fluid whole. But at the molecular scale, water is discrete, made of individual H2O molecules bumping around. The molecular description is more fundamental. But your experience of water as a continuous fluid is still real and useful. In exactly the same way, your experience of time as a flowing present moment is real. And the physical description of time as interwoven with space and gravity is also real. The second one is more fundamental, but the first one is not false. It's just operating at a different level of description. So what do we do with this? How does understanding this change anything? The first thing is this: your intuition is not a mistake to overcome. It's a feature. You should experience time as flowing. That experience is adaptive. It's useful. It's connected to real structures in reality. But now you know something more. Your experience is shaped by the scale at which you live. At different scales, time behaves differently. And that's beautiful, actually. It means the universe is not made of a simple, unchanging set of rules applied at every scale. It's layered. It's structured. The second thing is this: the fact that physics describes time in an unexpected way doesn't make time less real. It makes the universe more real, more intricate, more worth paying attention to. Your sense of the present moment, this now, is not an illusion. It's where you live. Where everything real happens for you happens now. You can't move to the future. You can't visit the past. All you have is this moment, and this one, and this one. And that's actually what makes time matter. Not because it's a flowing river, but because it's your path through the world. Every moment shapes the next. Every choice closes off some futures and opens others. Physics can describe the structure of that path in elegant mathematical ways. But physics can't capture what it means to walk that path. Only you can do that. So when we ask, why does time feel real, even when physics describes it differently? The answer is not that time is real despite what physics says. It's that time is real because of what physics says. Because time is woven into the deepest structure of the universe. Because causation is written into the rules of reality. Your intuition about time is not at odds with physics. It's getting at something true, something that physics tries to capture in mathematical language. You experience time because you're part of a universe that has time built into it. That flow you feel, that sense of causation, of moments becoming memories, of futures becoming real, all of that is real. Physics just helps us see the deeper architecture underneath the experience. And that's what makes it so fascinating. The question isn't, is time real? The question is, what is this thing we call time, and how is it woven into the fabric of existence? And that's a question that will keep surprising us.